Welcome to this walkthrough of LeetCode problem number 1029, two-city scheduling. In this session, we'll break down the problem, explore various solution approaches, and understand how to optimize our code. Let's dive in and get started. In this problem, we need to make decisions about sending people to two different cities, City A and City B, while minimizing the total travel cost. Each person has a unique cost associated with traveling to each city, given as costs I0 for City A and costs I1 for City B. The challenge is to divide the people equally between the two cities, meaning exactly n people must go to City A and the other n to City B. The objective is to find the minimum total cost required to achieve this division. The input to the problem is a 2D list of integers, where each subarray represents the travel costs for a person to both cities, and the output is a single integer representing the minimum possible cost of travel for the optimal split. Let's explore some examples to better understand this problem. Let's take a look at the first example. Here, the input costs list is 10, 20, 30, 200, 50, 40, 20, 30. Each subarray represents the travel costs for a person to City A and City B, respectively. The goal is to send exactly two people to each city while minimizing the total cost. The optimal solution is to send person 0 and person 3 to City A, and person 1 and person 2 to City B. Calculating the costs, person 0 goes to City A for 10, person 3 goes to City A for 20, person 1 goes to City B for 200, and person 2 goes to City B for 40. Adding these together gives a total cost of 10 plus 20 plus 200 plus 40 equals 110. This is the minimum possible cost for this input. Now, consider the second example with the input costs list: 259, 770, 448, 54, 926, 667, 184, 139, 840, 118, 577, 469. Here, there are 6 people, so 3 must be sent to City A and 3 to City B. After determining the optimal allocation, we send people 1, 3, and 4 to City B, and people 0, 2, and 5 to City A. Calculating the total cost, person 0 goes to City A for 259, person 2 goes to City A for 667, person 5 goes to City A for 577, person 1 goes to City B for 54, person 3 goes to City B for 139, and person 4 goes to City B for 118. Adding these costs gives 259 plus 667 plus 577 plus 54 plus 139 plus 118 equals 1859, which is the minimum total cost for this example. In the third example, the input costs list is 515, 563, 451, 713, 537, 709, 343, 819, 855, 779, 457, 60, 650, 359, 631, 42. There are 8 people, so 4 must be assigned to each city. The optimal allocation is determined by minimizing the total cost while maintaining this even split. After assigning the people to their respective cities, the total cost is calculated to be 3086. This allocation ensures the best balance between minimizing costs and dividing the people equally between City A and City B. To summarize, the problem requires dividing people equally between two cities while minimizing the total travel cost. Constraints include having an even number of people and each person having specific costs for traveling to both cities. Edge cases include scenarios like having only 2 people, large differences in travel costs between cities, or identical costs for all people. For instance, if all costs are the same, the solution simply ensures an even split of people between the cities. These constraints and edge cases help guide the algorithm to handle both typical and extreme scenarios effectively. To solve this problem, we first consider the brute force approach. Here, the idea is to generate all possible combinations of assigning 2 people to either City A or City B, while ensuring that exactly n people are sent to each city. For each combination, we calculate the total cost and return the minimum. While this method guarantees accuracy, it becomes computationally expensive due to the sheer number of combinations, which grows exponentially with the number of people. Specifically, the time complexity is O(2)(2n*) n, since we compute the cost for each of the 2(2n) combinations. The space complexity is O(n) to store these combinations.
However, the main drawback is that this approach is not practical for larger inputs due to the rapid growth and possibilities.
Next, we consider a greedy approach. Instead of evaluating all combinations, we look at the cost difference for each person between going to city A or city B, calculated as diff equals costs, I0, costs, I1. By sorting all people based on this difference in ascending order, we can assign the first n people, with the smallest differences, to city A and the remaining n people to city B, minimizing the additional cost incurred by these assignments. This greedy strategy works because sorting by the cost difference ensures that we send the individuals with the least additional cost to their respective cities. The time complexity of this approach is O, n log n, dominated by the sorting step, and the space complexity is O, 1, since no additional data structures are required beyond the input. This makes the greedy approach both efficient and easy to implement. One limitation, however, is that sorting can become a bottleneck for extremely large inputs.
Now, another option is the dynamic programming approach.
Here, we define dp, I, j, as the minimum cost to send I people to city A and j people to city B, considering the first I plus j people. The state transitions involve two choices: either send the I plus j1 th person to city A, updating dp, I, j equals dp, I1, j, plus costs, I plus j1, 0, or send them to city B, updating dp, I, j equals dp, I, j1, plus costs, I plus j1, 1. The base cases are straightforward. If we send all j people to city B, then dp, 0, j, is the cumulative cost for city B, and similarly, dp, I, 0, is the cumulative cost for city A. The final answer lies in dp, n, the minimum cost of sending exactly n people to each city. Analyzing the dynamic programming approach, its time complexity is O, n squared, since we compute values for all combinations of I and j. The space complexity is also O, n squared, because we need to maintain a dp table to store intermediate results. This approach guarantees correctness and is computationally viable for moderate values of n. However, a higher space requirement makes it less appealing when compared to the greedy approach, especially for competitive programming scenarios.
Ultimately, the strategy we chose is the greedy approach. It strikes a balance between simplicity, efficiency, and scalability.
By sorting individuals based on the cost difference between the two cities, we leverage the problem structure to make locally optimal decisions that lead to the globally optimal solution. This method is not only intuitive but also computationally efficient, ensuring that the overall cost is minimized without the need for additional data structures or complex calculations. While the dynamic programming approach provides a robust solution with guaranteed correctness, its higher space usage and relative complexity make it less practical. On the other hand, the greedy approach significantly simplifies the problem. Sorting the individuals by their cost differences allows us to minimize the total cost effectively while maintaining a time complexity of O, n log n. This balance of efficiency and simplicity makes it the preferred solution for both competitive programming and real-world scenarios. In conclusion, the greedy approach is the most effective strategy for solving the two-city scheduling problem. It allows us to arrive at the optimal solution with minimal computational overhead, making it a clear choice over the brute force or dynamic programming methods for this problem.
The problem we are addressing involves sending two n people to two cities, city A and city B, while minimizing the total travel cost. Each person has two associated costs, one for traveling to city A and another for traveling to city B. The challenge lies in ensuring that exactly n people are assigned to each city. To tackle this, we first consider the brute force approach. The first step is understanding the constraints. There are two n people, each with two costs, and we must divide them evenly between the two cities. Next, we generate all possible ways to assign n people to city A. For this, we use combinations to create sets of n individuals who can be sent to city A, while the remaining n automatically go to city B. This process ensures we explore every potential assignment configuration. Once the combinations are generated, the next step is to calculate the total cost for each assignment. For every combination, we sum the travel costs to city A for the selected individuals and the travel costs to city B for the remaining individuals. To track the minimum cost across all assignments, we introduce a variable, min_cost, initialized to infinity. As we evaluate each configuration, we update min_cost whenever a lower total cost is found. After examining all possible assignments, the minimum value stored in min_cost is returned as the result. This brute force approach guarantees an optimal solution because it evaluates every possible way to assign people to the two cities. However, it's important to note that this method has a significant limitation. The combinatorial nature of the problem leads to exponential complexity. With C(2n) combinations to evaluate, the approach becomes computationally expensive as n increases. To implement the brute force approach effectively, we rely on specific data structures. A combination generator, such as Python zittertools.combinations, is used to generate the possible assignments. We also use a variable, min_cost, to track the smallest cost encountered so far. During each iteration, temporary arrays store the assignments for city A and city B. While the brute force approach is exhaustive, optimizations can make it more practical. For example, early pruning allows us to skip evaluating a partial assignment if its cost already exceeds the current min_cost. Sorting the individuals based on the difference in their travel costs between the two cities can also lead to a more efficient solution, as it forms the basis for a greedy approach. In terms of complexity, generating all combinations takes O((2n) and calculating the cost for each combination takes O((n), resulting in an overall time complexity of O((2n) n. The space complexity is O((n), primarily for storing combinations in temporary assignments. This solution minimizes the travel cost by sorting the people based on the difference between the cost of traveling to city A and city B. The idea is to prioritize sending people to the city where the cost difference is smaller. The key equals lambda xx, 0, x, 1, sorts the list primarily based on this difference, ensuring that the most cost-effective assignments are made first. After sorting, the first n people are sent to city A, and the remaining n people are sent to city B. The logic is implemented in two loops, where the first loop calculates the total cost for city A, and the second loop calculates the total cost for city B. This approach guarantees that exactly n people are sent to each city while minimizing the total cost. The function then returns the computed total cost. This is the Java implementation of the two-city scheduling problem, LeetCode number 1029. The method two-city_sched mirrors the Python logic by sorting the input based on the cost difference between sending a person to city A and city B. Java-specific features include the use of the arrays.sort method with a custom comparator for sorting, and type declarations for variables and arrays. The solution calculates the total cost by summing up the costs for the first half of people to city A and the rest to city B. The problem requires us to assign 2n people to two cities, city A and city B, such that exactly n people go to each city, and the total cost is minimized. Each person has a specific cost for traveling to city A and city B, and we need to carefully distribute them based on these costs. Taking the example input, 10, 20, 30, 200, 50, 40, 20, 10, the first step is to calculate the cost difference for each person, which is the cost of traveling to city A minus the cost of traveling to city B. This gives us the differences, -10, -170, 10, 10. Next, we sort the array of costs based on these differences, in ascending order. After sorting, the array becomes 30, 200, 10, 20, 50, 40, 20, 10. At this point, we also initialize two variables, total_cost, which starts at 0, and n, which is the number of people to be sent to each city, calculated as half the length of the input list. Now that the costs are sorted, we send the first n people to city A. For the first person, the cost of traveling to city A is 30, so we add that to the total cost, making it 30. For the second person, the cost is 10, and adding this brings the total cost to 40. Next, the remaining n people are sent to city B. For the third person in the sorted list, the cost of traveling to city B is 40, so we add this to the total cost, resulting in 80. Finally, for the fourth person, the city B cost is 10, which brings the total to 90. Thus, the total cost for this example is 90, which is the minimum cost achievable under the given constraints. In the second example, the input is 259, 770, 448, 54, 926, 667, 184, 139. First, we calculate the cost differences. 259 minus 770 is equal to minus 511, 448 minus 54 is equal to 394, 926 minus 667 is equal to 259, 184 minus 139 is equal to 45. Sorting these by difference gives the ordered array 259, 770, 184, 139, 926, 667, 448, 54. Again, we initialize total_cost to 0 and set n to 2. To assign the first n people to city A, we add the cost of the first person, 259, to the total, making it 259. Adding the cost of the second person, 184, brings the total to 443. For the remaining n people, we assign them to city B. The third person's cost for city B is 667, which increases the total to 1110, and the fourth person's cost, 54, brings it to 1164. Therefore, the total minimum cost for this input is 1164. In the third example, the input is 515, 563, 451, 713, 537, 709, 343, 819. Calculating the differences, we get 515 minus 563 is equal to minus 48, 451 minus 713 is equal to minus 262, 537 minus 709 is equal to minus 172, 343 minus 819 is equal to minus 476. Sorting the costs by these differences results in the array 343, 819, 451, 713, 537, 709, 515, 563. With total_cost initialized to 0 and n set to 2, we first send the first two people to city A. The cost for the first person is 343, which we add to the total, making it 343. Then, the cost for the second person, 451, brings the total to 794. Finally, the remaining two people are sent to city B. For the third person in the sorted list, the cost of traveling to city B is 709, which we add to the total, resulting in 1503. The cost for the fourth person is 563, and adding this gives a final total of 2066. Thus, the minimum total cost for this example is 2066, achieved by this optimal allocation of people to city A and city B. This demonstrates the effectiveness of sorting by cost differences and dividing the assignments evenly to minimize the overall cost. To analyze the time complexity of this solution, we start with the sorting step. The costs array, which contains 2 n elements, needs to be sorted. Sorting such an array requires O, k log, k, time, where k is the size of the array. Since k equals 2 n, this simplifies to O, 2 n log, 2 n. Further simplification shows that the dominant term is O, n log n. After sorting, we calculate the total cost by iterating over the first n elements to assign them to city A and the last n elements to assign them to city B. These are 2 separate loops, each running n iterations, which takes O, n, time in total. However, since O, n log n, from the sorting step is the dominant factor, the overall time complexity of the algorithm is O, n log n. Next, we analyze the space complexity. The input costs array, which has 2 n elements, is part of the input itself and does not count as additional space used by the algorithm. Now, the sorting step uses Python's timsort algorithm, which may require O, k, auxiliary space in the worst case, where k is the size of the array. With k equals 2 n, this means the sorting step needs O, 2 n, space, which simplifies to O, n. Beyond that, the algorithm only uses a few variables, such as total_cost, n, and loop counters, which require constant space, or O, 1. Adding these together, the space complexity is determined by the sorting step, resulting in an overall space complexity of O, n. When comparing this optimized approach to a brute force method, the efficiency becomes clear. A brute force solution would involve generating all possible combinations of assigning in people to city A and n to city B. With C, 2 n, combinations to evaluate, the time complexity grows exponentially as approximately O, 2 n, n. n. This is computationally infeasible for large inputs. In contrast, The optimized solution focuses on sorting by the cost difference between the two cities and then greedily assigning the first n people to city A and the remaining to city B. This reduces the problem to sorting, which has a time complexity of O(n*log n). This is a dramatic improvement over the brute force approach, making the optimized solution far more practical. Finally, let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, even if the array is already sorted according to the required criteria, the sorting step still takes O(n*log n) time, as the sorting algorithm must verify the order. The cost calculation step adds O(n), but the overall time complexity remains O(n*log n). In the average case, the sorting step still dominates, as its complexity does not depend on the input distribution, making it O(n*log n). Similarly, in the worst case, where the input is in the least favorable order, the sorting complexity remains O(n*log n). Across all these cases, the space complexity remains consistent at O(n), as it primarily depends on the size of the input. This uniform behavior demonstrates the robustness of the solution. In this problem, there are several common mistakes to watch out for. One major issue is not enforcing the constraint that exactly n people must be assigned to each city. For example, in a brute force or greedy solution, it's easy to overlook this and end up with an uneven distribution. To avoid this, you need to explicitly verify the count of people assigned to each city in brute force methods or carefully adjust the logic in greedy approaches to ensure compliance. Another mistake is sorting by the wrong metric in greedy solutions. Instead of focusing on absolute cost differences, you should sort based on the relative savings or cost differences between the two cities. This ensures that the algorithm prioritizes the most cost-effective assignments. Lastly, overlooking edge cases can lead to incorrect results. Scenarios where one city's costs are much higher than the other, or when both cities' costs are identical, are examples of edge cases that should be included in your testing to ensure robustness. Now, another common pitfall is implementing an inefficient brute force solution. For large inputs, such as when n equals 50, the number of combinations grows exponentially, making this approach computationally infeasible. To handle this, you can either prune unnecessary paths while exploring combinations or switch to more efficient methods like greedy algorithms or dynamic programming. Misinterpreting the problem statement is another frequent error. For instance, failing to account for the requirement of exactly n people per city or misunderstanding the goal of cost minimization can lead to invalid solutions. To address this, it's important to thoroughly understand the constraints and clarify any ambiguities upfront, especially in an interview setting. Speaking of interviews, recognizing that this problem is a variation of the classic min-cost assignment problem can help you identify patterns and guide your approach. Be prepared to explain your thought process, such as why you chose a greedy method for simplicity and efficiency, and always validate your solution with edge cases. This demonstrates both technical skill and attention to detail. This problem also has connections to other optimization problems you might encounter. For instance, LeetCode 1029 is the classic version of two-city scheduling, while problems like LeetCode 1388, pizza with 3n slices, or LeetCode 410, split array largest sum, involve partitioning with constraints. Similarly, LeetCode 135, candy, is another example that uses a greedy approach to solve a constrained optimization problem. Beyond these related problems, alternative approaches to solving two-city scheduling include dynamic programming and backtracking. With dynamic programming, you can use a table where each entry represents the minimum cost to send a certain number of people to city A out of a given total. Although this approach guarantees the constraints are met, it requires more memory and can be less efficient. Backtracking with pruning is another option, where you recursively explore all combinations but discard invalid paths early, such as when one city exceeds its limit of n people. While slower than greedy approaches, backtracking might be easier to implement and understand in certain scenarios. Finally, the greedy approach remains a popular and efficient method for solving this problem. By sorting the list of candidates based on the cost difference between the two cities, you can prioritize assignments that maximize savings. This method is both fast and memory efficient, making it ideal for many cases. However, it's important to justify its correctness during interviews. You should be able to explain why sorting by cost differences leads to an optimal solution and how the algorithm ensures the constraints are met. While it may not handle every edge case as transparently as dynamic programming, its simplicity and efficiency make it a go-to choice for problems like this. Great job! We've successfully solved the two-city scheduling problem. Remember, understanding the core concepts like greedy algorithms and sorting is key to tackling optimization problems. Thanks for joining, and see you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!